Good evening, and a very warm welcome to all of you, a wonderful number of people who've signed up and joined tonight's lecture. It's kind of a Thanksgiving week lecture for those of you on the other side of the Atlantic, so a very happy Thanksgiving to all of you. Tonight's lecture, as you will know, is being given by Professor Vijay Balasubramanian. And he has been, for the last year, or was last academic year, our George Eastman professor here. And I should say, as many of you will know, it was such a complete treat to have Vijay and his wife Heather, who was also here as the Oliver Smithies lecturer, fellow for us last year. It was just wonderful for us to have them both here with us. Vijay, as you might detect from the title of today's lecture, is a Renaissance man. He is a physicist who is tonight venturing into the area of philosophy. Hence, Alex Kaiserman, one of our most distinguished philosophical fellows, is going to lead us through the Q&A. But Vijay has stepped out of the physicist mold into the philosophical mold. But while he was here, as some of you may know, he also took an interest in English bell ringing and how to play the gamelan. And I and other Balliol fellows had the pleasure of hearing him play the gamelan at the music faculty towards the end of his stay here. So, as I say, he enriched our life, as did Heather, wonderfully speaking. So just to say, I'm sure both during and at the end of Vijay's lecture, you will have all sorts of questions you want to ask. There's a Q&A function that you will see on your Zoom screen. So do just either jot in your Q&A questions or while the question and answer session is going on, add questions to that. And Vijay, I know, will be more than happy to deal with them. I should say I was thrilled when Vijay said one day over lunch that he was getting interested in Occam's razor and Duns Scotus. Occam's razor, because it's one of the maxims by which I've lived most of my civil service government life, and also when I was at the National Trust. Can we just find a simple way to do things? I know that is a great simplification of Occam's razor, but I have often applied Occam's razor in public sector decision making. Duns Scotus is very close to my heart because I frequently have spent summer family holidays up in the Scottish borders, from where Duns Scotus comes, and indeed have visited his memorial just outside Duns in Roxburghshire. So I will be delighted to hear what Vijay has to say about both these topics. Over to you, Vijay.
Thank you so much, Helen. I have to say, the last year at Balliol, for both Heather and for myself, was like one of the most magical years we've ever had. We keep talking about it constantly. So thank you very much for hosting us over the last year. And I will, and for this lovely introduction. And I will now try to share my screen to start the talk. So let's see. Is it coming up? Just about. Great. So this talk is, the title of the talk is Occam's Razor Revisited. Are simple explanations better? And this is the one of the Latin statements of Occam's razor, numquam ponenda est pluralitas, sine necessitate. You shouldn't posit a plurality without necessity. So I'd like to begin by talking about why I'm interested, why everybody should be interested in Occam's razor as a principle and what it is. So, all animals, and we're animals too, have to use limited information that they're able to gather, we being bounded individuals, and the limited resources we have to learn from the past and predict the future. It's an absolute necessity for life as an animal. This means that any animal must build inside its head some either explicit or implicit model of the world. You have to act predictively for what the future is going to bring. So scientists like me, of course, have to do this explicitly. It's part of the formal method to use your limited information to figure things out about how the world works and do that predictably. So I'm a physicist by training, And, we're conditioned by the history of our subject and the way we practice it to think that models of the world ought to be simple. And that's because we believe, most physicists believe, that there are underlying simple laws of nature from which the enormous diversity of phenomena that we see arise collectively. By contrast, biologists and social scientists who are really used to the immense diversity of the systems of life and of human societies and things like that, often think that models really do have to be very, very complicated, complex, in order to explain all these amazing phenomena around us. So really, I suppose the correct question is, what is the appropriate compromise? When should you build simpler models? When should you build more complicated models? And what are their relative roles? Now, just to make this as simple as possible, very often in the modern day, this is phrased in the language of, I have some data and I wish to fit a curve to it and describe the data in that way. So let me give a practical example, right? So for example, suppose somebody has two variables, x and y, and this could be any two variables, x could be the wealth and y could be, I don't know, performance in an exam or something, any kind of variable you want, and people will gather data, and the data will be these black points here, and they'll say, oh yes, if you have so much wealth, this is your performance in the exam. If you have so much wealth, this is your performance exam, and they'll plot it. And then they will try to infer, people will try to infer the underlying regularity, the underlying law of nature, if you will, from which this data arises. So let's think about what we could do. So suppose someone gave us the black points here. One person may say, well, actually, I think this, I could draw this blue line through the whole thing, and these black points are kind of, there should be lying on this line, but there's a little bit of noise or deviation for God knows what reason, and so really the regularity is this line. So that would be a simple model. A very complicated model is to say, well, I'm going to take a curve with many bumps in it, and I'm going to use those bumps to fit the data perfectly, right? So it'll fit the data perfectly. And you might think that such a model, this red curve, is a better model of the data because it fits all the data, it describes all the data perfectly. But look, if I extrapolate the red curve, it goes on like this, and the straight line goes on like this. So the simple model and the complicated model, if you will, make very, very different predictions for what's going to happen when you consider other values of things in this line, right? So they make very different predictions, and so we really do have to ask, what is the correct amount of complexity, if you like, in the models that we use to describe the world? And this has become extremely important now as we use all kinds of AI engines and things of this nature to describe phenomena in the world and then try to make inferences about what the future will be like. Now, one of the things that happens is that all agents, us as well as machines, who have to perform this kind of inference of some latent regularity in the world based on some limited data, they have limited resources. The data is limited, as I've already said. They also have limited computational power. My head is a computer, my brain is a computer, and it can only do so much. And that also applies to all the computers and laptops and everything else that people use. So it's a very, very important question in the practice of science, in the practice of all knowledge seeking, to ask if there is a trade-off between simplicity of models and the accuracy with which they describe the world, which is controlled by the resources available for the inference. So this is, for example, in economics, this is a very, very important question. How complicated does a model of economic phenomena need to be usefully predictive about the world and therefore guide policy, right? So more philosophically, and this is something that really matters to me, all theories that we are able to build about the world are going to be constrained by the resources of the computer in our head. So a question that's been sort of animating me since I entered college is, are there limits to our ability to understand the world? Is the intrinsic boundedness of my head going to limit my ability to, say, uncover the theory of everything, the full theory of nature? So for me, that's a very important question beyond the practical considerations being described above. Now, of course, we're not the first people to come up with this concern or this question. And famously, this very question was considered by William of Ockham, who lived between 1287 and 1347. And he's believed to have studied at Merton College between 1309 at Oxford, between 1309 and 1321. Actually, there's no direct evidence that he did, but everybody says that he did, and Merton would like to claim him, so let's give it to them, right? So here's Dr. Ockham, and he's in a stained glass window, and he became a leading scholastic philosopher. So there was many disputes about him. I think the Chancellor at Oxford tried to get him excommunicated. He ran off, he was Franciscan, and he escaped and was at the papal court in Avignon with other Franciscans. There he got into a dispute about the poverty of Christ, nearly got excommunicated, escaped to go and work at the court of the Holy Roman Emperor, and then wrote many, many important treatises in political philosophy and in things like the theory of property rights. So that's what he did during his lifetime. But later, in the centuries later, he became extremely famous for a principle of parsimony in reasoning. Right? So Occam's razor, as it's called, a razor for cutting through complications in arguments, in intellectual arguments, is often phrased nunquam ponenda est pluralitas sine necessitate, which means that plurality should never be posited without necessity. Now, last year, as the master mentioned, I was the Eastman professor at Balliol, and I thought, here I am at Oxford, this is where the man lived. I should go find out, go look at what he precisely said, since I just use it sort of all the time, this idea all the time. What did he say, and how did he use the razor precisely? So I began to dig through, and I asked, and he was at Merton, so I sent messages to the Merton librarian saying, could I please come and look at his works, etc., the original, and basically they had no time for me because they're all booked up. So then I asked the librarians at Balliol, and of course they also had copies of Occam's work. So I had a lovely, lovely time around this time last fall, so in October and November last year, ferreting through Balliol's amazing library and its medieval works. So here's a picture of a book. This is a manuscript of Occam's commentary on another famous book, which is the Sentences of Peter Lombard. This is made in the mid-14th century. Absolutely beautiful handwritten work. And it's very interesting to look at. Look, it's got lots of writing, lots of marginal annotations, lots of things like that. Really gorgeous. But gosh, what is it written in? I couldn't really read this because you need serious paleographic skills to make out what's written here. So that was a bit difficult. So then I asked Naomi and Stuart Tiley, who are librarians at Balliol, and they found for me in the Balliol archives down at the St. Cross Church this incunabulum, which means early printed work, which is a copy of Occam's commentary on the Sentences of Peter Lombard, and they have many other books that he wrote too. Now, what I found trying to go through this is it's really not easy to find specific references to the principle of parsimony, Occam's razor as it's called, in Occam's work. And actually, digging through commentaries on Occam, I found that some people claim that there's actually no references to Occam's razor in Occam's own work. But look, here is one of these early printed works, and if you look at this little bit of it and expand it and look at it carefully, there you go. It says right here, in intellectu, a bunch of stuff, quae, nunquam ponenda est pluralitas sine necessitate. So what this means is that he's explaining something or the other, and then he says, in the understanding that plurality is never to be posited without necessity. Now, I read that, and I thought, this sounds like a completely standard formulation. He's not saying, well, I have this idea that, you should not posit plurality without necessity. He seems to be saying, well, everybody knows, we all agree that this should be the case. So then he accepted it already. It was already there in the air, and someone else must have really pushed this idea before him. So I thought I'd go one step back and look at the work of Duns Scotus, who died, by the way, in the year that Occam entered Oxford. So he was also at Merton College, right? And he was a blessed, namely he has been elevated in the Catholic Church. And I would like to suggest to you that we should stop calling it Occam's razor and start calling it the razor of Duns Scotus, because the idea of explanatory parsimony is just all over the place in his work. Okay, so in particular, again, the Naomi and Stuart Tiley from the Baylor Archives found me a book, which is the Ordinatio of Duns Scotus. And so if you look here, for example, the seventh question of the second distinction in book 2 of his Ordinatio, it discusses the pressing question of whether an angel can be moved in an instant. So just to give some background, in those days, people accepted without question the existence of angels, and part of explaining the nature of the world was you had to explain the properties of angels. That's not intellectually unlike we accept the existence of quarks as components of protons, and we seek to explain the properties of quarks that explain the world. So it's that kind of inquiry, though whether we should accept the existence of angels is, well, most of us wouldn't right now. Okay, anyway, so he asked the question, while considering properties of angels, whether an angel can be moved in an instant, right? So there you go. There's the question. You can see there, Angelus ponit movenda in instanti, or something like this, right there, right? So he asked this question. So how does he answer this question? He says, well, to resolve this question, he says, we should first consider whether you should posit a different kind of time, a discrete time that applies to angels, while it does not apply to everyday things. And so to resolve this question, that's a valid question. It could be that different kinds of objects, experience time differently. And, in modern physics, people do think about that kind of thing. Is time experienced the same way by everything? Is space experienced the same way about everything? It's not a priori obvious that everything actually senses the world in the same way. So this is a good question, actually. So anyhow, so then he has some discussion and then says after a bit, dico ergo, and then a bunch of stuff, pluralitas non est ponenda sine necessitate. So the translation of the question, of his answer to this question about whether you need to posit an additional discrete time for angels, is that I say therefore to the question that a plurality is not to be posited without necessity, and there is no necessity why one should posit a discrete time that measures the motion of an angel, for whatever is secured by discrete time is also secured by continuous time in general. So what he's trying to say is that, well, look, if you want the angel to get from here to there in some sort of discrete instant of time without experiencing the intermediate times, you have no need to suppose that there's a separate kind of time for angels. You just say that the angel gets from this, from 0 seconds to 1 second and just shows up there, and you can say that, and you don't need to posit a secondary kind of time. Interesting. So this is, of course, a very satisfying application of the razor of Duns Scotus. And even though today in physics we still debate, as I've said, whether time, microscopic time, is actually continuous or not. Or whether time even makes sense as a concept at some fundamental level. So in fact, if you go through the rest of the questions in this book 2 of the Ordinatio, this kind of reasoning is there everywhere. So here are some examples of the questions that he's asking, right? So he asks, for example, whether an angel can be in 2 places at the same time, whether 2 angels can be in the same place at once, things of this kind. And we're apt to laugh at this kind of question. This is the angels and pinheads kind of question. And, there's an instinct today to say, oh, that's so funny. But it isn't. So today in physics, for example, it is a question whether 2 particles can be the same place at the same time. That is a basic question about fundamental particles. And the answer is, well, it depends. So there are 2 kinds of fundamental particles. There are particles called bosons, and 2 bosons named after the Indian physicist Bose, and 2 bosons can in fact be in the same place at the same time. So for example, the particles of light, photons, can be in the same place at the same time. The things that the things called phonons can be the same place at the same time. But other kinds of things like electrons which are called fermions, named after the Italian physicist Enrico Fermi, cannot be in the same place at the same time. There's something called the Pauli exclusion principle that say they can't. So in other words, this question, whether 2 angels can be the same place at the same time, it's a perfectly good question about fundamental particles in physics. It's just that well, angels is off base. This is all to say these are good questions, a little bit off base because of the times. But anyway, the way in which, for our purposes, the important point is that the way Duns Scotus makes his way through all of these questions is he keeps invoking his razor, and I'm going to call it his razor, Duns Scotus's razor, because it clearly wasn't Occam's razor, right? And he invokes this razor repeatedly to cut his way through all these questions. Okay, so now we know something. We know what our elders and betters declared. Fine, they said nunquam ponenda est pluralitas sine necessitate, and I use this idea all the time, right? So in fact, it's understood today as a kind of scientific rule of thumb that simple models are better, and the master just explained she used it as a rule of thumb to make better policy. Don't complicate things unnecessarily. But that's all good and fine, but why, right? I mean, why would it be that simple models are better? You'd like to know in some more, have an explanation for why simple models are better. We're using it as a rule of thumb and seems fine, but is there any actual evidence that you can use to argue in some precise way that simple models are better? So this was a question that for me, I had been thinking about from around the time I arrived at college, because physicists are going on and on and on all the time about, oh yeah, let's pick that model, it's a simpler model, and it works, right? Simpler models work better. And what the heck, right? There's no apparent reason why. So this is something I was interested in. So I'd like to illustrate why this is not so obvious what this is with a dialogue. May I ask Alex Kaiserman to please turn on his video too? Alex, thank you for joining us. Alex is a philosopher at Balliol, definitely more expert in all these topics than me. So I'd like to illustrate the problem with the idea of simplicity and complexity of explanations, which is what we're really talking about. What it means to be simple by using a slightly modified version of a famous paradox posed by Nelson Goodman called the new riddle of induction. So we're going to do this in the style of Galileo, who in his Dialogo sopra I due massimi sistemi del mondo, this is the one where he compares the Copernican system to the Ptolemaic system of the world. So there, in the style of the day, he wrote out dialogues in which you have people discussing options back and forth. This was a way of setting out an argument. So we're going to do this, and I'm going to be Simplicio, and Alex is going to be Sagredo. So let's begin. So this is to illustrate the problem with trying to define the notion of simplicity. So I'll start. I'm Simplicio. So Alex, things in the world are green or blue. For example, the grass is green and the sky is blue.
Actually, things in the world are grue or bleen. For example, the grass is grue and the sky is bleen.
What does grue mean? And what does bleen mean?
Well, grue means green until December the 31st, 2025, and blue thereafter. Bleen is the other way around.
That's just silly. You have no evidence for your theory.
On the contrary, I have just as much evidence for my theory as you have for yours, because our theories have both matched the data every day so far, and neither of us knows what is going to happen after December the 31st.
Okay, but your theory is still silly, because a plurality should not be posited without necessity. Your theory has an unnecessary arbitrary date on which the world changes.
Nonsense. Your theory is the overly complicated one. Look, I think the grass is grue and the sky is bleen, but you seem to believe that the grass is grue until December 31st and bleen thereafter, and the reverse for the sky. Why are you introducing an unnecessary arbitrary date?
Thank you, Alex. So you see, right? The moral of this story is both theories are equally complicated in the other's terms, right? So it's not so obvious to decide what is and isn't a simple theory, okay? So actually, I really started thinking about this very hard because a friend of mine who was a philosopher, so I was a graduate student at Princeton, where all the first-year graduate students get to live in the same dormitory, and you wind up talking to people across fields. And I had a friend of mine who was a philosopher, an analytic philosopher, and he told me about this paradox and started thinking, that is just crazy, and I need to sort this out because, it's just I really do want to make a theory of the world using, green and blue and, electrons and stuff that I can see. And if someone tells me that I could make it out of grooves and bleeds, that just, what am I supposed to do? Right, okay. So the question here is really, so if I were to make it as more precise, is there any circumstance, because there may be circumstances where you can't do this, but is there any circumstance where we can give a mathematically precise understanding for what it means for an explanation to be simple? So that's the question. So in fact, that became my first paper, academic paper, as a PhD student. This is my first paper during my doctorate. And I'm going to tell you a little bit about the history of it because there are lots of Oxford connections. So this was my first paper as a graduate student, but I was actually a graduate student doing, quantum gravity and string theory and things like this. And so this was completely off topic. And so my advisor said he didn't know anything about it, and he told me to go present it to Philip Anderson, who was a very famous Nobel Prize winner in the department. And Anderson had been away during my first year, and he had just come back. Well, so last year, we were staying in the Eastman flat, a flat that they give the Eastman professor at Balliol. And there's a board outside listing all previous Eastman professors. And what do you know? Philip Anderson was an Eastman professor. So he had just come back from being the Eastman professor when he chatted with me, and then he gave me $300 to go to a conference at the Santa Fe Institute. That led me to become an external professor today, probably helped me to become the Eastman professor at Oxford. And then that paper then got me a junior fellowship at Harvard because a senior fellow who had been a professor at Oxford also liked the work very much. So there's all of these sort of weird Oxford connections for me, associated with thinking about Occam's razor, including my own trajectory through this intellectual maze. Anyhow, coming back to our main topic. We're talking about inference in an uncertain world. This is recapping a little bit. And we have to act in an uncertain world. So we have data. We want to build models of that data, things we see in the world, and use it, right? The reason we need, and what we really want to know when we say we build a model of the world inside our head to do this kind of thing, what we're trying to get an understanding of is of the latent state of the world. It's not the data itself. It's the underlying model, the underlying truth or latent state of the world that we need to know, which is important for prediction, planning, and action. And this is true both for animals and machines. You infer current and future states of the world from noisy, corrupted, uncertain cues. You're never entirely sure what's going on. And to make matters even more complicated, the world is changing constantly, and you have to keep updating your mental model of the world. And then the mental model can be implicit or explicit. And reasoning can be formal or intuitive, but all of it requires resources. And there's going to be some trade-off between the resources and how well you can predict the future, how much data you can get. And so there must be some way of quantifying what the trade-offs between these things are. Okay, so that was what my first PhD paper was about. So let me tell you a bit about it. So I'm going to put a bit of math on this page and a little bit on the next one. And I'm going to do that because even though that is not usually done in a public lecture of this kind, that's because I think it's really important for everybody to understand that this isn't talk, just talk. This is also, formal reasoning in mathematics. And it's really important sometimes to understand, so the attitude I have to this kind of thing, presenting mathematics in public spaces like that, is that, we have cars that run. And it's not magic. Underneath the hood, there's an internal combustion engine. It works a particular way. Everything's hooked up in particular ways. And we can all understand that. And understanding how that works is part of what gives sort of control of the world. So here I want to tell you a little bit about the reasoning that underlies what I'm going to tell you in a moment. So suppose someone gives you a data set, some set of data drawn from the world. So these are E1 through En. These are supposed to be N examples of data from the world. And suppose I ask you, please decide, was this data generated, produced by a probability distribution, right, in family A or B? What do I mean by probability distribution? Lots of things are governed by probability distributions. So for example, an example of a distribution is if I pluck a random person from the population and I ask you, what is their height going to be? You can't tell me for certain, but you can tell me the probability that they are 5'4", 5'5", 5'6", 5'7", because there's lots of statistics about this, and you can use those statistics. So there's a rule that says that if you want to work out the probability that given the data you saw, that the truth about the world is A versus B, you can work that out using a rule called Bayes' rule, which relates that probability of the world being like A, given the data, to be the probability that a world like A would generate the data E. Right? So that's a formal relationship that was originally devised by Thomas Bayes, who was an English statistician, philosopher, and Presbyterian minister. Now, Bayes was interested in questions like, is there a rational basis for law? Right? For example, could you assign in a sensible manner a probability to whether or not someone stole that loaf of bread? Things like this. He was interested in these kinds of questions, and that partly led him to this kind of analysis of probabilities and likelihoods and statistics. So on the right side here, there's also two other terms. There's what's called the prior probability of A and the prior probability of the data. So the prior probability of A means before you see anything, you may have some prior belief why green and blue is a better model than green and blue. You may have some prior beliefs, and those prior beliefs are encoded in this bits, in the prior probabilities of these things, of the possible models A and B of the data. And so the rule is you're supposed to choose the model A of the world if the probability of the data given the model of given A is bigger than the probability of the data given B. And then you're supposed to do some, this is an integral, there's some integrals and some fancy formulae, and those of you, this being Balliol, the Balliol alumni, some of you will know information theory and this, that, and the other, and you'll recognize what these equations are. It doesn't matter so much for us. There is some set of equations like this that you can write down and do a formal analysis of the likelihood that a given set of data was generated, let's say, by some model A or some model B. Now, after some work and manipulation, you can manipulate that into a formula like this. That is quite a mouthful. And what I'm going to do is I'm going to explain qualitatively what this formula is trying to say. For those of you who are actually mathematicians, statisticians, and everything amongst the alumni, you can read the line on top and see what these different terms include. But for the rest of us, let me go like this. On the left-hand side, this is basically the probability that the model you're considering generated the data. And I have in front of it a function called a logarithm. If you know what that is, great. If you don't, ignore it. It doesn't really matter. Right? And then on the right-hand side, there are 1, 2, 3, 4 different terms I've written down. We're going to go through each one and explain the qualitative meaning. So what we're trying to explain here is formal probability theory gives a meaning to the notion of complexity and accuracy. So we're going to explain the meanings that probability theory assigns to the notion of complexity. So that's what we're going after. So on the left-hand side, there's the probability that your model generated the data. Now the first term here is a term that rewards models that describe the data better, namely assign a higher likelihood to the observations. If you wish to visualize this, you can think about this like this. So here I'm drawing the space of all truths. T is the actual truth. Now the data you get, you draw some data from it and it'll be a bit noisy, there'll be a little cloud there. And when you say which model fits the data better, you're really asking, well, here's the red model. There's actually many models in it, depending upon how you choose the parameters. Which model should you pick? Well, the one that comes closer to the data, that fits it better, is the one that you're usually led to pick. So that is the first term here. It's a reward for describing the data well. So probability theory says you should definitely like it if your model describes the data well. And so you get a reward for that. It increases the likelihood that the model you've picked is true, that it's describing the actual latent truth about the world. But then there's a second term here. And the second term here, D, is the number of parameters in the model. So this term is a penalty for having more parameters, right? So for example, if I have a model with one parameter, I've drawn this here, or a model with two parameters, I've drawn it as a two-dimensional thing, because this, let's say, is one parameter and going that way is another parameter. then, somehow the one parameter model is more constrained. You've made more of a commitment to what you think the truth is, right? And this makes less of a commitment to what you think the truth is. So in that sense, the one parameter model is clearly less complicated, right? It's simpler, I would say, right? Following Occam, we may say that this has two parameters, this has one parameter, all else being equal, a plurality should not be posited beyond necessity. So this model, which has two attributes or parameters, well, you should, unless it's actually justified to pick the two parameters, you should stick to the one parameter model. So this is a precise mathematical penalty for having more parameters, and therefore it favors simpler models. The third term is also a penalty for being overly complicated. So for example, imagine, like we were drawing earlier, that you have data, which are these black points, and what I'm trying to do is and there the data line, the unit square, and what I'm trying to do is to develop a model of the latent thing from which the data was drawn. Okay, the latent function from which it was drawn. So I might say, well, all of this data actually came from this red straight line, and that's my simple model of the data. It more or less fits everything, but not quite, And then suppose somebody else comes up with a space-filling curve, a very, very wiggly curve that just sort of fills the whole thing up. It fits the data perfectly. Well, which should I pick? Both of them have only one parameter, because this is a line, and this is also a line, albeit a very wiggly one. But clearly it's more complicated. This wiggly model is clearly more complicated than the straight line. So in what sense is it more complicated? Well, this next term in the expansion here given by probability theory gives you a specific penalty, a specific quantitative mathematical penalty for models that are overly expressive. It tells you should favor models that aren't so expressive, that are more constrained and make less, and therefore, are less able to fit everything, right? So then one more term, the final term here, favors models that are more robust and penalizes models that are less robust. And that is also a kind of complexity. Let me explain that. So suppose you have a situation where this is the truth, and here's one family of models, and here's another family of models, A and B. Now, the model B, if you pick this parameter here, comes very close to the truth. It's an excellent description of the truth. But if there's any noise at all, or if you mess up in any way with picking that parameter, you'll be toast. It's a terrible description of the truth. On the other hand, model A doesn't come very close anywhere, but it doesn't matter. There's some slop, right? You can pick the parameters in many different ways, and it'll give you roughly equally good a description, which is very helpful. That makes it much less complicated as a model. I don't have to sweat and gather huge amounts of data and be super precise to find out what the model of the truth is. I can just get a little bit of data and get a kind of more or less approximate model, and it'll all be equally good. So in that sense, model A is definitely simpler, and therefore should be preferred unless you have enough data and resources to somehow pick out the special point. And this last term in this expansion that comes out of probability theory is precisely favoring models that are simpler in this sense. So all of this is to say that that probability theory, in a very precise way, actually says that the razor of Duns Scotus, there's a version of the razor of Duns Scotus, well, Occam's razor, whatever, is realized, right? So mathematics tells you that you should indeed favor simpler models, and these things in the math are the penalty for being too complicated. Okay, so that was a bit of a mouthful. So let's step back. So that was theory, as in that was mathematical theory, and it's just related to probability theory, not particularly related to the world per se. So there's an interesting question here to ask, whether people or learning machines, like all the AI engines we talk about, whether they actually prefer simpler explanations when performing intuitive model selection. So Occam told us, or Duns Scotus told us, that we should prefer simpler models. And those of us, who go to universities and all this kind of thing, we do all kinds of formal reasoning, and we may incorporate this preference for simple models. Apparently, the thing that probability theory tells us to do, right, that we may incorporate this preference for simple models into our practice of how we describe the world. But most people don't do that. We all go around the world and we do many things, and there's lots of intuitive and automatic selection of models of the world. Certainly babies have to do this all the time. They haven't gone to university either. They haven't heard of Occam or Duns Scotus. So the question is, when people perform intuitive model selection on an everyday basis, do they have a simplicity preference or not? And we now know what simplicity preference should mean precisely, right, in a context where you're doing probabilistic inference. Likewise, you can ask whether, if there is a preference for simplicity, whether humans and machines have the same bias towards simplicity that is considered optimal by the probability theory, by the mathematics. So those are two questions that you could ask. So recently, this is something we thought about. So you can make up a scenario. Now, this is the kind of scenario that cognitive scientists make up, and then they present to people and get them to do these kinds of experiments and then try to test these kinds of cognitive biases. So here's a kind of a thing you can do. So these dots and lines are supposed to be flower beds, okay? So you tell the person doing the experiment, the participant in the experiment, that you have these flower beds. And then you say to them, there are two flower beds. One has a flower. The flower can be anywhere in the bed. Over there, it can be anywhere. And I'm going to tell you that it drops 10 seeds, and the 10 seeds are these red dots, okay? And I'm going to tell you that those 10 seeds are kind of distributed randomly. They sort of float around, right? The wind sort of blows them around a bit. And they're kind of distributed randomly over some region near the bed. And, we did this with human subjects, with 50 subjects for each task and 500 trials and so on. But anyway, you can give them one of two tasks. One is to say, you can ask them, which bed contained the flower? And this is a question that's asking the person to infer the latent cause of the seeds falling where they are, right? And so the flower could be anywhere in this bed, and you're trying to infer that it's in this bed or this bed, so the latent cause of the appearance of these seeds on the ground, right? There's a second task you could ask, which is, just tell me which bed is closest to the seeds, right? This is just the facts, ma'am, kind of approach, right? I mean, so I'm not asking you to infer the latent cause and think about it and think about where the thing could be. Just take all the seeds and tell me which is closest, right? That's the second thing you could do. Just for clarity, going back to these kinds of expressions, the second task, which tell me which is closest, is just saying pay attention to this first thing, which tells you how well you fit the data. And the second task, the first task, which says infer the latent cause, is implicitly telling you pay attention to how well you describe the data, but include whatever your implicit penalties for complexity are, or use your bias for simplicity if you want to. So that's what this is trying to say. All right? So, great. So what can you do? Well, so these days, there are many claims about machines that also are intelligent, and so if you accept that, then they have some kind of machine cognition, and you can ask whether machines have cognitive biases too, just like people. That's a perfectly fair question to ask. So how do you ask such a question? Well, here we had humans participating in an experiment, so now we need a machine that participates in an experiment, right? And we wanted to participate in the same experiment. We want to give it these pictures of the seeds that have fallen out of flower beds and tell it, please infer for me the present it with these two tasks. Okay, so here's the way you can do this. So those of you amongst the alumni who have done machine learning will sort of recognize this picture. For the rest of us, I'm going to try to explain what this is. Okay, so this is what I'm describing here is a standard kind of architecture for neural networks that people are using these days. And so I'll try to explain what this architecture means and what you're supposed to do to train a machine to do a cognitive task like inferring the flower bed, and then how that works. So what you do is you take, let's say, the picture of the flower beds, the two alternative flower beds, and the data, and here's the data of where the seeds came. And you have to first get this picture, which is the thing that you showed the person, into the machine. So to do that, you pass it through what's called a convolutional neural network. A convolutional neural network you should think of as the analog of the retina in your eye. When you see something, in comes the data from the world, all the photons, all the light lands on your eye, and the eye has some very complicated 3-layer neural network in it. Literally, right? There's 60 types of neurons arranged in a 3-layer neural network. And what comes out the back is the output from the retina coming through the optic nerve is are what are called visual features. So you don't actually transmit the light that appeared everywhere in front of the eye. Instead, you check for the presence of bright dots or dark dots or red dots or green dots, or for things that are moving from left to right or from right to left. There's various kinds of visual features. So you take the image and you piece it apart into its sort of component, interesting pieces, and that's what you transmit over the optic nerve to the head. So the convolutional neural network is an artificial way of doing that kind of thing. So anytime you have a computer vision system or a system that answers your voice when you talk to it, it has a layer like this in front that's taking whatever comes in from the world and it takes in whatever comes in from the world and converts it into a set of sort of more or less comprehensible or useful features. You don't transmit everything, only the useful stuff, the thing you want to do. So then the next layer that's being described here is something called, well, there are two bits. One here, this thing here is called a variational autoencoder. So a variational autoencoder in the trade is an object that takes the input that's coming in. So this is this kind of features extracted from the visual world that you present and converts it into an internal encoding. So it's an internal latent description of this. This is like, from the eye, when you go back to the visual cortex in the back of your head, what you know about the world is all contained in these firings of all these neurons in your head, right? They have an encoding. They encode the world in some way. It's not literally the world. It's an encoding that represents it faithfully. So this variational autoencoder, you can see from the terms autoencoder, it encodes itself. It encodes the input. And so it has a nice way of representing the world inside the machine. Then you pass it through what's called a multi-layer perceptron. The multi-layer perceptrons go back decades. This is your basic neural network architecture, where you have a layer of artificial neurons, then a second layer, then a fourth layer, third layer, fourth layer, and a bunch of layers. And then what you want this to do is to classify whether it thinks this data came from this flower bed or this flower bed. So that's the basic architecture, and then some more details over here. This additional piece is to make sure that you don't care whether the flower bed, sometimes the image presents the flower bed to the left and sometimes to the right. So all this kind of slightly details are irrelevant. And this piece is supposed to take care of removing the irrelevance of stuff like it doesn't matter where the flower bed is in the screen, all that kind of stuff. Okay, so that's the full architecture. So this is a very standard kind of architecture. It's the kind of thing that people use all the time. All of us have now experienced AI engines doing stuff, and underneath the hood, it may be something like this, right? Just like underneath the hood of your car, there's an internal combustion engine. So anyway, you're supposed to train this, just like you would train a baby to do stuff, or the human, when they're trying to learn this task, they need some training, so they do lots of practice trials. In the same way, you do lots of practice trials, and you tell it when it got it right, and when you tell it when it got it wrong, and then it adjusts its internal architecture to do it right, okay? So then you have your mock human, if you like. You have a machine that can do the same cognitive tasks. I remind you that there are two tasks. One is you have to infer which the latent cause of the seeds, which bed contained the flower. And then the other one says, just tell me which bed is closest. Okay. So now I'm going to explain the result. Okay. So this is a summary of the result. So it's a complicated figure. So let me explain it bit by bit. So in this figure, the way things are drawn is that everything has been written in some sort of notation, whereby this blue line tells you is a measure of having zero sensitivity to all these complexity penalties. Right? The dashed orange line is what the complexity, which is taken at the value 1, is describing how strong your penalty for complexity should be if you're doing it optimally according to probability theory. That's what this orange line is telling you, right? So here the scale, notice, has been stretched out. I really should have put them on the same scale. But anyway, this is 0, and this is 1, this is 0, and this is 10. So keep that in mind. So this line here describes the complexity penalty that the math would tell you for having many parameters. This line is, let's just ignore this for a moment. I didn't talk too much about this. This line is telling you the complexity penalty for having overly expressive models, like, instead of having a straight line, you say it's a very wiggly curve. And this line is telling you the complexity penalty for robustness or lack thereof. So what you learn from these pictures is regardless of which task you give the human, whether you tell them this Bayes is supposed to be inferring, let me make this bigger. This is supposed to be the task that infers the latent cause, and the lower one is just the closest bed, is what these two tasks are supposed to be. And what we're seeing from this is that humans, regardless of what you tell them to do, always use a complexity penalty. They don't use as much of this one. It's harder for them to estimate that. But for the others, they are definitely biased. Humans are biased in intuitive model selection towards picking simpler models, even if you tell them, by telling them to do this, to ignore the complexity of their mental model of the world, right? Even if you tell them, just tell me the closest flower bed, they're unable to get rid of their bias towards simpler descriptions of the world. By contrast, if you train up neural networks pretty much learn the optimal complexity penalty. Notice humans have a huge penalty that they impose over here, for having overexpressive models, too many parameters, right? We really prefer simpler models. And so we have a gigantic penalty for having too many parameters, if you like, or overly complicated models. Whereas machines learn pretty much precisely, the correct optimal penalty for complexity according to probability theory. On the other hand, if you tell the machine, listen, ignore that and just tell me the closest flower bed, they learn it basically perfectly. They have almost no penalty for complexity. So in other words, you can instruct a machine to not have a bias towards simplicity, but you can't instruct a human to do that. We just prefer simpler descriptions of the world as people. Okay, so that's what this is showing. Let me end. So the first thing is I'd like to say this: perhaps Duns Scotus was right? That first of all, as a matter of principle, probability theory has a built-in razor of Duns Scotus. So this is also an appeal to stop calling it Occam's razor, because clearly we're misattributing this, and it was at least Duns Scotus. Maybe he got it from somewhere else, but at least it should be Duns Scotus. Anyhow, so probability theory does have a built-in razor of Duns Scotus, and it's true that simpler models are preferred by the probability theory, and they're preferred until there is enough data to justify using a more complex model. And what's more, probability theory and the mathematics predicts specific quantitative penalties for added complexity. So it's very precise. The second thing that I described to you is that humans have a systematic bias towards simpler models and away from the most likely choice, and these reflect the predictions of probability theory. But that machines can learn the optimal simplicity biases in inference and model selection tasks. So machines can do it optimally. Humans just have a systematic bias. And humans and machines reject these simplicity biases when they're trained on tasks where a bias to simplicity is suboptimal. But we humans just can't get rid of this bias towards simplicity. It's just baked into our heads. So it's just a thing in how we think. Our cognition is different from the machines. So let me finish by talking about what can you do with this further. So this is a lot of fun. I think it's a really wonderful thing that we continue to think about these kinds of ideas that were first discussed, in the 1300s at Oxford. They're still extremely relevant, and we just achieve over the centuries, over the millennia, we achieve higher. We make the thought more and more precise and clear, and we're able to use it in more practical ways. So one thing we've been thinking about is, one of the reasons why these kind of simplicity biases matter to humans is because the computer in our head is bounded, right? So because of that, as described by the mathematics, if you've got limited amount of data you can work with, limited computational power, then you need to use a simplicity bias to avoid sort of making mistakes or picking the wrong model or an overly complicated model. And so it turns out that there is a law of diminishing returns relating accuracy and computational cost. It's just true that if you throw twice the amount of computing power in your head or in a machine, or twice the amount of data, you're not going to get twice as good a result in your inference. It's going to be better, but it's going to be less than twice. So there is this law of diminishing returns, which we discuss in this work, and that matters, right? I mean, because we don't have arbitrary resources in the world, either for humans or for machines. So you have to invest the resources in relation to the expected gain. And so that's part of what's going on in the importance of using these simplicity biases. So another reason why I think this is important is if you think about all the learning engines that people are building today, ChatGPT being one of them, it's just incredible how much money and power is being poured into these things. So, for example, the 3 Mile Island nuclear power plant here in Pennsylvania is being turned on again, apparently to provide power to a Microsoft data center, which they're going to use to train AI engines. This is insane, right? I mean, the planet is not going to be able to afford so much power expended on turning these machines. Personally, I think the future of AI is not in these kinds of gigantic engines, but in actually very small devices with little artificial brains in them, which have to make do with the resources they have, the little bit of power they can gather, the little bit of data that they can gather, and to make inferences on the fly, because that's what we'll really want to do, and that's where things will go. And so these kinds of simplicity biases will become very important, even for machines that are trying to do inference. On a more philosophical level, you could ask, given that humans and machines, well, humans certainly, have bounded resources, why are we able to learn anything? Why aren't we always swamped by how complicated the world really is? So there's something hidden here about the structure of tasks that can be learned, right? You can't learn everything because you've got bounded resources, but some things can be learned. And developing from the kinds of things that we said today, it's possible. This is some work that's ongoing with some friends in computer science. You can start characterizing the nature of tasks that can be learned given a bounded amount of computation and data. And basically, it has to be simple enough in some sense. The task has to be simple enough to be learnable. And so there's an argument to be made that all the things that we as humans want to learn happen to be the tasks that are learnable given the constraints of our head. And that's why the machines can learn them too. We've picked tasks. It's not that everything is learnable. It's that some things are learnable given bounded resources. And those are the things we care about. The rest of it is just acts random anyway. We can't learn it. So that's something that I'm thinking about. And I would say that that's a much evolved version of the ideas of people like Duns Scotus and Occam. And finally, there's another kind of thing that, again, about the practice of science and of the intellectual endeavor, which involves what I would call the role of toy models. So I've talked about simple and complex models, right? But as a physicist, a very common thing for physicists to do when they're faced with a new, very complicated system that they want to describe is to come up with what they will call a toy model. A toy model is an extremely simplified kind of model of the phenomenon, which typically really doesn't contain many of the details. It's like extremely simplistic. It's like a balls and springs kind of model of, I don't know, a human social phenomenon, right? A completely crazy level of simplification. And they'll call it a toy model to emphasize that it really isn't the real thing, and it isn't the real thing. And it's astonishing how often these kinds of toy models and thought experiments lead to extremely useful insights in both the sciences and the social sciences. And that's because for many phenomena, it turns out that a very stripped down toy model description is sufficient to give you insight into the qualitative origins of a phenomenon. And often that's what you want. Like, as opposed to, for example, the detailed mechanisms that are realized in the system. Let me give you an example. Water is this nice liquid, but you go to 0 degrees centigrade, and the crazy thing freezes. It becomes a solid. A solid is completely different from a liquid. And so you can ask two kinds of questions. One question you can ask is, heck, why does water freeze? Why does anything freeze? That's nuts, right? How can a liquid become a solid? That's one kind of qualitative question. And then you can ask a precise question, right? Why does water freeze at 0 degrees centigrade? And those are different kinds of questions. You can answer the first one, why does anything freeze? using a toy model and get a qualitative insight of the phenomenon. And then you can ask the precise question about 0 degrees centigrade, and that you need to get a much more complicated model of the molecule, water molecule, and how it interacts with other water molecules. So there's this recognition that, which is also, I think, related to the kinds of things that we were talking about today, and Occam's razor and the razor of Duns Scotus and so on and so forth, about the role of this kind of simplified reasoning, simple descriptions in unveiling the qualitative nuggets about the world that we really care about. So that's something that I'm continuing to think about with an economist at Balliol, David Vines, because in things like, in the social sciences especially, extremely complicated human phenomena, it's important to understand these distinctions between simple models, complex models, and toy models, and the different uses they have in the intellectual endeavor of describing the world. So I'll stop there for now.
Thank you so much, Vijay, for that fascinating talk. We are open to questions, so please do post your questions into the Q&A box. We have a few great ones already, so I will kick things off. We have a question from Tony Kluder. I hope you won't mind if I paraphrase Tony. So he points out, I think this relates to our little dialogue we had, Vijay. So he points out that people use different categories for the same situation at different times and from different points of view, and that categories themselves have different ranges of what's included in them. And he asks, how is this understanding included in the concept of simplicity? So I suppose, is there a sense in which some categories are simpler than others? Or like with the little dialogue we did, are we always forced into a situation where from the perspective of one person, one set of categories seems simpler, whereas from the perspective of another, a different set of categories seems simpler?
So I have some thoughts on that, and Alex, you probably have comments on that too, from the things that from the philosophical perspective. So I don't think, first of all, I don't think this question is resolved as to whether when you're describing categories to describe the world, whether there's any absolute sense in which one is simpler or the other. I don't think that's actually completely resolved. What can be the case is I could take a sort of instrumentalist point of view to say, look, as far as I'm concerned, what I'm going to do with this concept is this particular flow of reasoning. Like, for example, if I'm solving some set of equations, I start with something and there's a series of logical moves I do that mathematics tells me I can, it's supposed to get me to an answer. And that all I care about is that for that restricted, sequence of things I need to do, it should be easy. There should be fewer moves that I have to make, things like that. And from that point of view, it could well be that that some categories are easier to use or simpler to use than others. So in the case of green and green-blue, well, if I have to keep saying this is GRU and that means on December 31st something will happen, blah, 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 that might be complicated. But if all I want to know is I want to get a can of paint that matches the sky or the grass, I'll say, well, this is this color. I'm going to name it green. We make no commitment to anything else. That's good enough for me. And you might say, well, it's actually GRU. I'll say, well, I'm not trying to tell you a truth about the world. I'm telling you right now, instrumentally, what it's like, and then I want to compare it with something else. So that's a very instrumental answer. And physicists, and I'm one, will often retreat into that kind of thing. Like, look, I'm just a carpenter in the world, and all I want to know is, does the saw work? I really don't care about. And that's just a way of hiding away from the broader question, which I think is legitimate, and in fact, I think is not resolved. I have one more comment about that, actually. So your comment has a relationship to something that's become very important in the last 25 years in fundamental physics, called the notion of duality. So the notion of duality in physics has to do with the following thing. So you have some physical system. Let's say it's described by electrons and some set of symmetries and something or the other. It can turn out that that same system has a completely different description in terms of magnetic monopoles and some other symmetries and some other stuff. It can even happen in some situations that you have a theory, a world described, let's say by 3 plus 1 dimensions, like us, 1 for time. So it's 4 dimensions, 3 space and 1 time. So it has 4 dimensions, it has stuff like that. And then it turns out that everything you calculate in it can equally well be calculated from a different world which has 5 dimensions, right? So in other words, there is a dictionary that relates every observable thing in this 4-dimensional world to every observable thing in that 5-dimensional world. So which is it? Is it 4 dimensions or 5 dimensions? Right? Is the world made of magnetic monopoles or electrons? Since you can do equivalent descriptions, that's a little bit like Grubline and the green blue. That's one of the reasons why I care about that philosophical conundrum. It's practical. We face this on essentially everyday basis in some kinds of theories of physics, especially in quantum gravity. So the way in which so there are various ways in which physicists think about that. So one way of approaching it is, well, which description you choose to give depends upon which question you want to answer, and use whichever one makes the answer to your question easy. They're both equally good. They look different, and that's fine, right? Different descriptions can exist for the same phenomenon, and that's perfectly fine. It's just a description. It's a phenomenon that counts. You have to compute the observables, is the way physicists would describe, or measure the observables. And so long as it describe them, knock yourself out, buddy. Use whatever language you like. Would be the thing. And typically people will use the one that's easiest for them to calculate it, right? Sometimes the answer is given like this. It says that there is in fact a deeper theory.
Right.
And that deeper theory has in it a true description, a fundamental description, but it has different limits. And in this kind of limit, you can describe it more easily using 4 dimensions. And this limit, it's easier to describe it using 5 dimensions. So use the description. Since we're limited beings, use the description that for us is easy. But there is a deeper thing that you should really be going after. That's the fundamental theory. So there's a 2 class of answers. I hand it over to Alex because I'm sure he'll have comments about this.
Well, I was going to say, I prefer the second explanation, but that might be my bias as someone who's undergone philosophical training. Talking of which, actually, Peter Telford notes that the bias of simplicity is reflected in the fallacy. If I don't understand something, it must be either untrue or unimportant. And this, I suppose, is related to a question from Sam Trivedi as well, who asks, in physics, is there a distinction between simple explanations and simplistic explanations? If so, is there any way to tell the two apart prior to experiments, observations, etc.? So I suppose the general theme here is sometimes the bias to simplicity is conducive to the truth, helps us abstract away from noise and our data and so on. And sometimes it might be something that leads us to overly simplistic answers. Is there any way, as scientists or indeed as human beings, that we can tell apart these?
Yeah. Yeah, that's a very interesting and important question, because very often indeed we have, as we said, human beings have biases towards some simple explanation of the other. I mean, this kind of thing often happens in things like people's ideas about medical treatment, right? And it's often easier to talk about some very simplistic idea that, I live near the, understanding the function of vaccines can be very difficult. And so you instead say, well, that doesn't work. If I inject myself with some compound or the other, it's a sort of magic bullet. There's a lot of reasoning like this that picks the simpler explanation over the more complicated causal explanation that's actually there. So of course, as you know, the method in not just in science, but in all of our intellectual disciplines is you're supposed to come up with an idea, simple or complicated, whatever it may be, and then test it. The test is supposed to involve saying something about something you haven't yet looked at or you haven't measured and saying, do you get it right? And if you get it right, then the simplification you had was useful. And if you get it wrong, well, it was not useful, at least for this particular measurement. Now, the important one subtlety here is that if you pick a simpler explanation than the truth, it's going to be wrong on some things. So you need to understand the limits of the explanation also. So to check yourself from doing something too simplistic, you have to compare what the explanation says with things that are there, right? Do you get them wrong? Now, and then you have to then build on that to say, well, you'll get some things wrong. What things do you expect to get correct using this simpler explanation? And do you get those things that you expected to get correct? And if not, maybe it was just going in the wrong direction to do this. So the example of the water that I was giving earlier is a case in point, right? You can make up very simplistic models where you have, the water molecule is like a little ball. It has some sort of attractive interaction with the thing next to it. You make up some number for it, and then you say, well, you heat it, you cool it, this, that, and the other, and you try to describe what happens. There's nothing like what a water molecule looks like, right? H2O has an oxygen and two hydrogens, and they have particular angles. They have van der Waals forces. There's lots of details there. So you can make this up. And then you can say, well, I understand but then, to be honest, you'd have to say, I understand full well this isn't water. I'm trying to say, what would happen if I had many, many, many objects with some sort of weak ability to attract each other? Qualitatively, what would happen? So if you build a simpler model, you will be able to explain the world in a coarser way. And you have to have some ability to sort of navigate that. How coarse can the explanation be? How coarse do the phenomena have to be? And how do you recognize failure of your explanation? So this is also something that the last 50, 60 years of physics have been very concerned with. That's because, there are many branches of physics. There's fundamental theory of nature and what have you. But there's also lots of physics that studies materials, like, electronic materials, wood, all kinds of stuff. You want to understand the properties. And of course, you're not going to go try to explain the properties of a bar of iron, starting with quarks and leptons and, the strings of quantum gravity, whatever. It's much better to have a much more higher level predicate. Like, I have an iron atom, right? You'd prefer to use much higher level things. It's just a waste of time talking below that. So you use those higher level predicates, but then you understand that in some systematic sense, you arrived at those higher level concepts by in some systematic way, approximating over, coarse graining over the more the finer details. And you'd like a way to say, here, if I remove those finer details and kind of approximate them away, what is the correct higher level concept to use? So there's a systematic way of building that up. So that goes by the trade name, the renormalization group, quite a mouthful, but it's really a systematic way of doing this. So physicists are very fond of this as a formal procedure that's possible in some systems for revealing how the microscopic description, which may be truer but more complicated, gives rise to a simpler but more effective and useful, coarser, simpler description. Mm-hmm. Applying this kind of, it's a very beautiful thing, but also it's very difficult to apply precisely in most systems. So if you try to apply the renormalization group to society to derive the laws of economics, there's not going to be a very easy way of doing this. But as a conceptual thing, it's useful as a way of thinking about what it means to have coarser or simpler models and finer models.
Mm-hmm.
Do you think
that
answers the question? Yeah, sorry.
That was great. This is a conversation we have in philosophy too all the time about whether toy models, which are deliberately stripping away certain kinds of complexities, can be explanatory, and when they're too simple or too simplistic, and when they are in fact getting the right level of coarse graining to explain. There's reminds me that the joke, why did the chicken cross the road? Well, first we must model the chicken as an incompressible sphere. So yeah.
Yep. Yes, exactly. So
I like this question from Saad Hamid, who suggests there might be a connection between Occam's razor and aesthetics. So just as Occam's razor says the explanation or theory should be just complicated enough to explain the data but no more, a criterion for whether something is beautiful is that it can't be improved by adding anything or taking anything away. Interesting structural similarity.
Yes.
So invite some comments on that.
Yeah, that's such a beautiful idea. That is a really beautiful idea. And so I have so many different comments about that. Now, first of all, different people and certainly different cultures place the bar about when you shouldn't add anything more or remove anything in different places. Mm-hmm. So, for example, Japanese art favors a certain kind of aesthetic that is very spare and that has also been very prevalent in modern art, right? A kind of spareness. So you focus on just the thing that's there, like the pottery is just a round thing with maybe a little divot in it, and that's it, right? Something like that. Baroque art, Indian art has often favored a much more elaborated aesthetic with lots of decorations in the art, right? But there's such a thing as too much, right? If you add too much, it just becomes so busy and you can't see anything or understand it at all. But I suspect that people from Japan would find much of Indian art, perhaps a little bit further along that line in the first place. So I just want to make it clear that, of course, clearly different people could put the bar in different ways. But I completely agree with you with the statement that when you have a great piece of art or something that, or it doesn't even have to be art. I take a very expansive view of what is art. So, for example, I think decorative arts are arts. I think furniture building is art. Things like this. Lots of things can be art. It does give you the sense that you shouldn't add anything and you shouldn't remove anything. It's just right. Just leave it alone. There's this kind of sense like that. And I feel that way a lot about music, actually. So there are some modern composers whom I can't listen to very easily because I find they just have too much stuff in it. There's things going on that I don't understand. And because I don't understand them, it's just too complicated for me to be able to put it together into a picture. In a like manner, I actually don't like Beethoven at all, right? Because I just find the music just too full of stuff all over the place. And I can't relate to it, right? Bach I like, but sort of weirdly, for that reason, I still like Impressionist music, which also has a lot of stuff going on, but it's a different kind of lot of stuff. But that said, so those are just sort of random comments because I haven't really thought about aesthetics. But I think it's a really beautiful idea, and I think there are these trade-offs, right? So I've also heard people talk about trade-offs, like how to say. So the master mentioned that I played gamelan last year with the gamelan troupe. It's an orchestral kind of music, and I note that if you look at orchestral traditions like the gamelan or the Western orchestra versus Indian musical traditions, they sort of trade complexity in a different way. So in Indian music, there's just so many different scales, right? So South Indian music has 72 parent melakartas, those are modes, and out of the 72 modes, there are so many different ragas that you can write down, scales of different kinds. North Indian music has traditionally 10 of these parent modes. They're called tats, and then many, many, many ragas that come out from each one in various ways. But Indian music tends not to be orchestral. So the musician can focus on the complexity of the mode and the scale and how you elaborate them and how you play with them. Whereas I think Western music tends to have, and also gamelan music has a more limited number of scales because you're so busy dealing with everybody else and trying to coordinate with them. So I think there's sort of this limit of how complicated a thing can be for a human being to deal with it, right? And so we trade that complexity in different ways to make the thing interesting.
That's fascinating. It reminds me of a claim. I'm not sure if it's true that the complexity of a language is related to how many times a country's been invaded, and so therefore how many times speakers of a language have had to make themselves understood to other speakers. So the more isolated a linguistic community is, the more complex the language becomes. And conversely, perhaps people in the audience will be able to correct me if I'm mistaken on that, but there's a similar analogy there, yeah.
That's a very interesting idea. Like, for example, there are many trade and Creole languages which have at least start out with simpler linguistic structures because there's all of this other stuff they have to deal with at the same time. Whereas, but many of them, I think, over time are going to become more complicated again. I think there's a human tendency to add a certain amount of layers of complexity to these things. Yeah, it'd be very, very interesting to study this. Like, there are languages with all the nouns are declined and all the verbs are conjugated. The other languages that don't do that, but then they'll have 12 tones that you have to deal with. The complexity goes into something.
Yeah. A question from Christopher Curry. I guess on the first part of the talk where we were tracing the razor back further to Ockham, I should note we have at least one person advocating for keeping the name Ockham's razor. Don't elaborate on why. It has a certain ring to it, I suppose.
Yes.
But Christopher points out that if one can understand why we'd be if we were bounded by the resources of Balliol Library, we would be able to trace the razor back to Duns Scotus and no further. But is there reason to think that really this idea that I guess that we should always opt for the simpler explanation, all else equal, is present in intellectual thought even before Duns Scotus and perhaps in other traditions before that?
So there are definite antecedents. So, I stopped at Duns Scotus because that's like what I could get my hands on, so to say. Also, in fairness, come on, we have to give the guy more credit. Can't all be Occam. So that's the way I felt after reading this. It was this kind of sense of, I've read a paper and I've been writing about this guy's work for years, and I discover, wait, it was there in the paper that he got it from. I should have been citing somebody else. So it was that sort of sense of an academic thing. But there were definite antecedents. So St. Thomas Aquinas has, he doesn't quite phrase it in this way, but this idea of simplicity in reasoning is useful is there in Thomas Aquinas. Aristotle, in some of his works, he doesn't articulate it right as a catchphrase, and doesn't articulate it as a thing you carry in your back pocket and wheel out every time you have a complicated set of reasoning to solve. But it's there, it's implicit in these earlier authors too. So from that point of view, it's not clear exactly who one should attribute it to. In fact, one might further say, there's no new idea under the sun. Almost anything we come up with, someone thought of in some form before, right? Atoms were thought of by, early people. And those early people, was it Parmenides, whoever it was, amongst the Greeks? I'm sure, that idea was there in, in the hunter-gatherers who migrated out to the African continent. Somebody thought, well, everything is made of stuff, right? So I think there are many antecedents. So I agree that there's a question as to how to, if you want to attribute it, who we attribute it to. One possible elegant solution, besides not, it's nice to have a catchphrase, is someone suggested to me that I should try to start a movement to dub the thing Merton's razor. Because, at least two people were from Merton. There were lots of scholastic philosophers there. The Merton people will be very happy, and then probably go around talking about Merton's razor, and then you could start a movement, because more than one person is using it. I thought that was a very clever idea. I wonder what people think of that. But anyway, I do agree that there are certainly antecedents. I have not personally. So one of my, if I should ever get a few months back in Oxford, well, I could do that here too, but I'm always so busy. A thing I would love to do is to trace that history. Right? I'd like to know, what variants of this idea cropped up in things like Thomas Aquinas and Aristotle, and no doubt many, many thinkers in between. It would be a fascinating thing to do, to see how this idea of simplicity in reasoning, parsimony in reasoning, has played its role over centuries. And certainly Oxford would be the kind of place to do it. People in your department, Alex, must know some.
Absolutely. Well, we hope you'll come back and do that work. I'd be interested to find out as well. We have a question from Steph K, who asks, how, if at all, does the panpsychist philosophical worldview interact with the razor? So panpsychism is the view that everything is conscious. So not just human beings and certain complex organisms, but electrons and protons are conscious too, albeit in some more primitive sense than we are. And you might well think, well, why would anyone take seriously such a ridiculous thing? And I think it's actually sort of plays into the themes of the talk to some extent too, because there's a sense in which this view is much more complicated than the view that just humans and animals, certain animals, are conscious. But another sense in which it's simpler, because panpsychism doesn't have to explain how consciousness emerges from purely non-conscious stuff coming to be arranged in particular ways. It can, well, at least some people think it has a simpler explanation to why consciousness arises in the first place. If atoms and electrons are conscious, and they come to be arranged in certain ways, and they give rise to more complex kinds of consciousness.
Okay.
So I suppose the question that might emerge from that example is, how do we trade off these different kinds of simplicity when we're thinking about what the simplest explanation is?
So actually, I think this is an excellent question, and thank you, Alex, for explaining panpsychism so clearly and the idea. So let me. So I have many thoughts about this, and also another kind of dialogue-y kind of thing that I like to pose to my students about it. So I'll tell you about both of those. So the first thing is consciousness, like the meaning of quantum mechanics, is like one of the major unsolved problems of our day. We don't understand what measurement theory in quantum mechanics should really mean, collapse the wave function. That's a technical thing. But if you ask somebody, what does it mean to be conscious? Well, I haven't heard a definition that I understand or subscribe to completely. Right? If you ask neuroscientists, there'll be, some people try to define things in terms of some type of global activity in the brain, this, that, and the other. There are many kinds of consciousness. Well, you can argue back and forth, and maybe it's good and bad, what they've done. Okay, so I think, first of all, the notion remains for me unclear and ambiguous, and there may be different kinds of consciousness. Second, I would say, partly because I was born and raised in India, as opposed to in the West, a prior bias, I suppose, towards the notion that consciousness pervades more things than just humans, right? So at least in the Hindu Buddhist part of Indian culture, I would say that there's less of a distinction recognized between humans and at least other animals, right? That is to say that that's just more of a continuum. So they're like us, we're like them. We're just a bit more fancy, is the idea. And I do think modern science would say that. Like a dog is less fancy human. Certainly chimpanzees are almost human. They're not quite there in terms of their cognitive ability. So I do think that there's a continuum. So you can just continue down this line, humans, chimpanzees, dogs and cats. Somewhere down there are beetles. Beetles probably have feelings. They use the same neuropeptides that we do to produce states like fear, right? I mean, so they probably have feelings. We just don't recognize them very well. And so it sort of keeps going down. And then this is the usual kind of argument where does the thing stop being conscious? Are plants conscious? Well, depends upon how you define it. Maybe plants are conscious. Maybe all living things are conscious, depending upon how you define it. But then you keep going and you say, well, the living thing is made of pieces. The pieces are made of pieces. And all the way down, you've got atoms. Well, heck, where did it stop being conscious? Right? That is a very good question, actually. So, and I would say there are two kind of classes of explanations that one could kind of try to give for that. And so one is the kind of atomic kind of explanation, which is that the components contain a piece of the whole, and that you assemble them, and if you assemble more of them, they have more of the stuff, and eventually that stuff becomes sufficiently complicated, etc. You might describe it. That's a sort of atomic explanation. Then there is the kind of emergence style of explanation, that the phenomenon you're describing is not implicit in the pieces, but in the relationships between the pieces, right? And that and so indeed, in the relationship between three things, there's a certain degree of whatever, of the thing that will eventually become akin to what you're calling consciousness, right? So there's a kind of pathway in those relationships. Both of them feel problematic when I'm talking about three atoms talking to each other. I really have a hard time accepting that they're conscious. On the other hand, I recognize that I have 3 atoms, then I have 50 atoms, then I have 1 billion atoms, I have a mole of atoms. I keep going. At some point, it's and then I rearrange the atoms a little bit, and then a little bit more, and a little bit more. And at some point, it's my head, right? So where in that process did it become? So these are there are many famous discussions, like the ship of Theseus example in philosophy of you keep replacing the wood and Theseus as a ship, and eventually, when does it stop being Theseus as a ship? So it's sort of akin to these kinds of reductions where you simplify the system or you change the system a little by little by little. At what point did this discrete change happen, or is it a continuum? Personally, I subscribe to the idea that it's in the relationships, that it's not in the atoms, it's not atomic, it's in the relationship in things, that there's something emergent in that sense out of the relationships between these objects that produces consciousness. One of my difficulties here has to do with the definition of consciousness. I don't have a good one, and I've been for many years trying to work my way towards one that would be satisfy me. It'll satisfy nobody else. It's a sufficiently complicated thing. Nobody's going to agree, but whatever would satisfy me, and I haven't been able to arrive at one. I also think that to some degree, the things we say about consciousness, if we're not trained like Alex as a philosopher, tend to be largely linguistic. So, for example, sometimes my students have done this thing where I tell them, look, I think a rock is conscious. Prove me wrong. And then students say, well, what do you mean a rock is conscious? I'll tell them, how do I know I'm conscious? And then very often an answer a student will give to me is that you can change your mind. Right. I don't think that is a good definition of consciousness, by the way, but that is often given to me as an answer, right?
Yeah.
You have a mind and you can change it. You can choose something else. Whereas, mechanical objects always do the same thing, no? Right? They're always, you put the ball here, it rolls down. It doesn't have a mind. It's not conscious. Okay. So here, I'm going to prove to you by your definition by this definition of changing your mind, that a rock is conscious, right? So you take a rock, you hit it with a hammer, it goes bong. You hit it with a hammer again, it goes bong. You hit it with a hammer again, it splits into two. Oh my God, it changed its mind about what it should do. And then if you probe me further, I'll say, well, look, what happened is that every time you hit the rock, there was something in the internal relationships between all of its atoms that changed. Sure, it rang, so the coarse effect was this ringing sound, but inside it, something changed. That's no different from what happens inside my head, right? You slap me once, I turn the other cheek. You slap me a second time, I turn the other cheek. You slap me a third time, I'm sick of this. I slap you back, right? I changed my mind, right? But really what happened was inside my head, there were lots of neural firings, the state changed a little bit, and at some point I just got sick of it, right? And sick of it is some state of my neurons. What is the difference between that and the rock changing its internal state? Now, there is some difference, clearly, right? But I don't know how to put words to it very clearly. So that's what I mean by saying consciousness is often, I think, linguistic. And I think the way we use the term consciousness, it's going back to the simplicity, complexity thing. It's at some level, a simple one-word encapsulation of some extremely complicated phenomenon that allows us to make heuristic decisions about how we will relate to things we consider conscious versus things we consider not. So it's a sort of binary distinction we try to make. But I agree that I'm not sure that there is such a binary distinction, though I do not tend to the atomic description of that.
Fantastic. Okay, well, it's gone 6:30, so I think we should wrap things up there. Sorry to those whose questions I didn't get to. It only falls to me to thank Vijay again for a fascinating talk, and to all of you for attending and for your questions. We will be back in the new year with another set of lectures. I hope you'll join us for those. And indeed, all of our past lectures are on the Balliol YouTube channel if you'd like to catch up on those. A wonderful collection of varied talks. Thank you so much, Vijay, again. That was wonderful.
And if I might say thank you, Alex, for hosting. Thank you to all the participants for taking your time to show up. And thank you to Balliol for hosting this thing. And finally to the master for the very kind introduction.
Thanks, everyone. Have a good evening.